this, what's this note over here on the left side?
I think that says start with 0.
All right. Hold on just a second. By starting with 0, he moves like that.
Something like that.
Okay. And a lot of times that's what you have to do to be able to come up with that nth term. And I realize this is just a sequence. It's not a series. Let's draw circles and see if we can discover anything. I did notice one thing here, that there's one chord and there's 2 regions. That's the next term. You put a second chord on there and there's now 4 regions. That's that term.
Yes, sir.
And you put another chord on there and there's going to be 7 regions. 1, 2, 3, 4, 5, 6, 7. So I see what he's doing with the chords and the circles, but I don't know how that gets you your nth term or the general term. I experimented with a lot here. Obviously, the one thing you notice, the one thing to do is to figure out differences. Okay, well that difference is 1, that difference is 2, that difference is 3. We found our sequence. The next one is 4, the next one is 5, the next one is 6. So I could tell you the 7th or the 11th term, but translating this into an expression of n. First of all, this tells you that since that is linear, 1, 2, 3, 4, 5, 6 is linear, that's an arithmetic sequence.
Yes, sir.
Then it indicates that the underlying sequence is quadratic in nature.
Yes, sir.
Which means you probably need a term on the order of n squared or n minus 1. I experimented with all kinds of them, and I couldn't come up with one that worked. But you'll notice that is quadratic. You end up with an n squared.
Yes, sir.
Has your teacher taught you how to do this? Because none of the math books that I have give you a method for doing it.
Let me see. I'm trying to see if I can remember this properly. Let me see. A_n equals a_n squared plus b_n plus c. Okay. So it looks like for a quadratic, we have a_n equals a term n, a subscript.
A sub n, okay.
A sub n.
Equals what?
Equals a_n squared.
A sub n squared?
Plus just regular n squared. Plus bn plus c.
And A, B, and C are what? Because that's kind of the sequence that I was fooling around with, and I couldn't get it to come out to this sequence. I would say A has to be 1, because that's the first term.
Wait a minute. Oh, I think I remember this.
If you can figure out one of them, I think we can figure out all of them.
So what it looks like, what you do, we may need, all right, can we go to like a clean sheet?
Sure.
Because we may need more room for this.
Yeah, hold on a second.
I can't remember exactly why this works the way it does, but maybe once
Doesn't
we
matter.
do it, it'll make
Doesn't
more
matter
sense.
why isn't important. If you can figure out the method, that's what's important. I don't know the method. It's always been tricky for me. I've always had to kind of guess and check and see if that's the sequence before I finally discover it. And there's got to be a better method than that. But go ahead. You want me to write that sequence out?
Let's do, I think there's another sequence. There's 3, 7, 15, 27, 43,
Hold on.
and so on.
3, 7,
3, 7, 15, 27, and 43. Okay, so the first thing, like what you were doing, we find the gap between each of the terms. So it's going to be 4, 8, 12, and 16.
Okay. And that tells
And then
that that's
we,
linear. In other words, because that is linear, 4, 8, 12, 16 is linear, it's an arithmetic sequence, that makes the underlying one quadratic.
yes, sir. And so the difference, like, because of that, the difference between those are 4.
Okay.
Because, yes.
That means one of our terms has to be n plus 4, or?
Now, since this is quadratic and we had the equation a sub n equals a n squared plus bn plus c, the idea...
Come up with 3 equations and 3 unknowns.
Yes, sir.
Because we know what the first term is. So 3, a sub 1 is 3, so
that makes 3 equal to a plus b plus c.
hold on. How do we get that? Oh, because n is 0?
If we plug in n equals 1, I think with this one we're just going to start with 1.
Okay.
We start with a1. So that means...
So a plus b plus c is equal to the a sub n.
Is equal to... That's right.
The first term, so that's equal to 3. Okay. Now what? Now we plug in 2 for n.
I think there
7 must equal 2a. When we plug in 2 for n, hold on. I think I'm going to get this. This technique seems like it's going to work. Okay, so if I plug in 2 for n instead of 1, then I got 4a plus 2b plus c equals 7. Am I on the right track?
Yes, sir.
If I plug in 3 for n, that's 9a plus 3b plus c equals 15.
Yes, sir.
There's 3 equations, 3 unknowns. We should be able to solve for a, b, and c.
Yes, sir.
Which means we'll have a sub n equals like 2n squared plus 3n plus 4, something like that. And that will be our nth term.
That's right. Something like that.
That's the way to do it. This I've never, at least not in the last 10 years, have I had anybody explain how to do this.
I think I think there is,
This key right
I
there.
think that way,
And
I
that's
think
only if
that way's
it's a
right.
quadratic, right? If it's a cubic, you probably need an cubed plus bn squared plus cn plus d
That's right.
on the other ones.
That's right.
Okay.
I think there's a way to
Shall
sort
we,
of.
shall we solve this? This is actually not that hard to solve. Because we have a plus c in all three equations, we can
Yes, sir.
subtract 1 from 2 to eliminate c, and then we can subtract 2 from 3 to eliminate c, and we'll have two equations with just a and b.
Yes, sir.
Should we do it?
Sure.
Let's try it.
Yes, sir.
Then I want to figure out how you take that quadratic and write it simpler. Because usually you don't see a quadratic as the answer. You see something like n times n plus 1. All right, so let's see. Let me label these things. So I'm going to start 2 minus 1. So that gives me 3a plus b equals 4, correct?
Yes, sir.
Now I'm going to do 3 minus 2, which gives me 5a plus b equals 8. And now I'm going to subtract the bottom one minus the top one, which gives me 2a equals 4, a equals 2.
2.
We know that is a 2. And if b must be minus 2,
Yes, sir.
we got 2n squared minus 2n. And now c has to be 3. So there is our nth term. Let's just check it with the first few terms here. When n starts out 0, this thing is 3. Or
Yes,
1.
sir.
We can start it out 1. Well, I guess we should start it out at 1. When n is 2, we have 8 minus 4 plus 3, that's 7. When n is 3, we have 9. 18 minus 6 is 12 plus 3. Beautiful. That is the technique. Well, thank you. I learned something new every day.
Yes, sir. I think there was, and it's interesting that we did it that way because it connected back into another way. I think the idea with this other way that I knew, this just involved, I guess, having this on hand, because what you would do, you would plug in n equals 1, n equals 2, and n equals 3 into the equation.
Right.
You would get a plus b plus c, and the and 4a plus 2b plus c, and then 9a plus 3b,
which is
plus
this,
c.
right? That's what all that is.
That's right.
No, I love this. So let's go back here for a moment to your questions. So that is a quadratic, so we can do it using that technique.
That's right.
And hold on, I can't get my thing to work. There we go. Now, I'm guessing this is not quadratic because we're going from 2 dimensions to 3 dimensions. Let's see, what do we get? We get 1, 2, 4, 7. Notice we get that sequence, which we know to be quadratic. That's the above sequence.
Yes, sir.
So this has to be cubic.
That's right.
Which means a sub n has to equal an cubed plus bn squared plus cn plus d. And we're going to generate 4 equations and 4 unknowns.
That's right.
I got to tell you, I haven't solved a 4 by 4 in 10 years, 40 years. They take so long to do. You can do them using matrices, I suppose. You sure they used A and A? I think this is a little confusing. Maybe I'm wrong. Should that be A or should that be X, Y, and Z instead of A, B, and C?
Yes, sir. They use A.
They do use A. Okay. Huh.
But I think there's a difference between the two.
I could have used, in other words, I could use X, Y, and Z and still solve it.
Yes, sir.
X, Y, Z, and R, any variables. I find it confusing because I don't think there's a connection between that first coefficient and A sub n. A sub n has a very definite meaning. Okay.
Yes, sir.
So anyway, the way you determine whether it's quadratic or cubic is by taking the differences and finding that's linear. It's going to be linear in all 4 of these problems at the bottom.
That's right.
Over here, if we take the difference, you'll notice we get 10, 26, 48. Well, now you got to take the difference again to realize you get 16, 22, and I'll bet the next one is 28. Let's see. In other words, this has to be quadratic.
Yes, sir.
In nature. And I don't have any doubts that it will be because they've labeled all of these as cubics. So we know if we take the difference between each term, we're going to end up with a sequence that is a quadratic sequence.
Yes, sir.
This second problem is a cubic. Oh,
that's right.
Clever, pretty clever. That's cubic. This is quadratic. This is cubic. This is quartic. Which means your first term, yeah, quartic means this is going to have to be an AN to the 4th.
Did you say quartic?
Quartic.
Quartic.
Yeah, that's a spell like that. Quartic. Quartic is a 4th degree polynomial. The cubic is a 3rd degree polynomial. Quadratic is a 2nd degree polynomial.
Okay.
Okay. And you'll study quartics and cubics if you haven't already, and figuring out how to factor them. But 4D space, it's interesting how he connects that to just a quartic. Yeah.
Yes, sir.
Okay. It's not hard to find the next term in any of these. Well, the only thing that's difficult is finding that general term. But now I know how to do it. Terrific. Thank you for teaching me something.
Yes, sir.
So do we need to go through any of the rest of these?
Do we want to do like a cubic?
We can do a cubic. It's going to be much harder to solve the 4 by 4, but let's...
well, then do we want...
as long as you... Well, we could get it started. Okay. So let's get it started using the general. Hold on.
Well, which would you have recommended?
Well, the only problem with doing the cubic is it's going to give us 4 equations and 4 unknowns, and that's going to take us a while to solve. 3 equations with 3 unknowns, where one of the unknowns is plus C plus C plus C, those are really easy because you can get rid of one of the variables very quickly. I don't know that I can, I've never, like I said, tried to solve a 4 by 4. I think I could. What you do is you lose one of the variables, and then you have a 3 by 3, and then you lose another variable, and you have a 2 by 2, and eventually you solve for one variable and work your way backwards to solve for all 4. But it's tough, At a very minimum, let's do 9 and let's get it set up.
Yes, sir.
So the general we know is going to be what?
So that's a sub n equals a n cubed plus b n squared plus c n plus d.
And then give me 4 equations.
Okay, so we have, and if we are going, okay, so I think we have to start with,
So
start with 1.
Let's always start with 1 and see if that gives us the first term.
Okay,
And sometimes you might have to start with 0, but that's usually something that's exponential in nature. As we know that a sub 1 is 4, so 4 has to equal what?
a plus b plus c plus d.
And 14 has to equal
8a plus 4b plus 2c plus d.
And 40
27a plus 9b plus 3c plus d.
And finally 88
64a plus 16b plus 4c plus d.
I'm sorry, 64a, I got lost at that point, but now I see.
Plus 16b plus 4c plus d.
Yeah, notice how these count up. Goes
Yes.
once the first term is hold on a second. This goes 1, 4, 9, 16, which is 2 squared, 3 squared, 4 squared. So this must be 2 cubed, 3 cubed, 4 cubed, which it is. Yeah, it's 1 cubed, 2 cubed, 3 cubed, 4 cubed. And then you get to the C term and it's linear. It goes 1, 2, 3, 4.
Yes, sir.
What do we do next? Or what would we do next?
We're going to make 3 equations.
Okay. Doing what?
So we're going to subtract the first from the second.
Okay, let me label them. Try to keep everything positive when you do these.
Yes, sir.
You probably don't want to subtract the fourth from the second. You're going to subtract the second from the fourth.
Yes, sir.
See why? You're trying to lose the d, so you can lose the d going either way, but if you do 2 minus 4, you end up with a lot of negative coefficients and numbers. So
wait, the first from the second?
Or you can do 2 minus 1. We'll start there. That's really easy.
All right.
So this is equation, we're going to end up with 3 equations. The first one is 2 minus 1. So what do I get?
So that's going to be 7a plus 3b plus c.
See, we keep all of our coefficients positive this way. And that's equal to 10. Okay? Now we can use any other 2. We just can't use the same one again.
Yes, sir.
So what's another good one to do?
Subtract 2 from 3.
Okay, so 3 minus 2, which is going to give us our second equation. What is that?
19a plus 5b plus c is equal to 26.
Okay, we only need one more. Where's it going to come from?
So 3 subtracted from 4.
Okay.
So that's going to be 37a plus 7b plus c is equal to 48.
Okay. And now you can follow it to its next logical step, which is to lose c.
Yes, sir.
And you will then have two equations with a and b. Solve
Yes,
those
sir.
two equations using elimination also, and you will solve for a, and then you'll solve for b, going backwards, and then you can solve for c using one of these three, and then you can solve for d using one of these four. So,
Yes, sir.
what a tedious task that he's giving you here. There must be a faster way to do it, and I kind of see what it is.
Is it just to have all the different equations on hand?
I think it has more to do with the fact that this coefficient is 1 cubed, this is 2 cubed, this is 3 cubed, and this is 4 cubed. This is 1 squared, this is 2 squared. Can you see 3 squared, 4 squared?
Yes, sir.
So we could kind of quicken it up, I guess. If we just recognize that, we wouldn't have to substitute 1, 2, and 3 for n. But whether that gets you directly to the nth term or not, I don't know. I don't see it myself. No, I don't see anything but doing it the hard way. But surely he didn't mean for you to have to do what we're doing right now for 5 of these problems. Each one of these problems is like a 15-minute problem, correct? Doing it the way we're doing it.
I think what he wanted us to do was to just have the basic format of all the different equations for each of the terms. Then you find the differences of each equation, because it's going to be the same for each cubic problem. And then you just, because if basically what it is, like what we did, we plugged in N1, N2, N3, N4, and we got those 4 equations.
Right.
Then we got the 3 other equations from there. So take away each of the, what they're equal to, the 10, 26, and 48. And that's going to be the same for any cubic problem. But the 10, 26, and 48, that's the difference between each of the first layer of terms. So then when you get the next 2 equations, they're going to be equal to the difference between each of the 10, 26, and 48. And then the final equation is just going to have one term, and it's going to be equal to the difference between the 10, 26, and 48.
Does that give us a shortcut for coming up with the answer, the nth term?
I think the idea is just to have it that for a cubic, the thing where you get one term, I think it's always going to be 6a.
What I'm thinking is that it must be something like this. What is that first difference? 10. We know it's a cubic, so there has to be another n in there. And if we took the difference, that would be 10, 26. So maybe something like that, and proceed like that if that is possible. Not that that's the answer, but I think they prefer, or if there is a quick way to get to the general term, you're going to get to it like that, not as a put together cubic thing. But I might be wrong, guessing. But I just can't imagine he would force you to do all of the work that this method that we found, and that's the only method I know of at this moment, to come up with the general term. So you want to go on to another page? I'm not sure how much more I can add to this.
Sure.
We can come up with the general term. It's just an unbelievably tedious and long method. And I'm thinking there must be a shortcut somehow. But I don't know. This stuff here is fairly easy for me. All right. So the key equation on all of these is that top one.
The top one, A equals PERT.
That is continuous growth. And that you are surrounded by that. Everywhere you look, it's how bacteria grows. It's how populations grow. It's how radioactive material decays. Same equation. Just that this is negative when it's decay. And just to write this out, it's P, the way I remember it is PERT.
PERT.
Okay. And when you have continuous growth, R is your rate of return. So this first problem we see down here, it's compounded continuously, so we can use PERT. Okay, so let's do it.
PERT. Yes, sir.
Hold on, something funny is happening here, but okay. So if we start with A equals PE to the RT, where both the R and the T are in the exponent. P is your starting amount. R is 0.0825 for this problem. And here's what we're looking to do, is we're looking to triple, right? So the amount we want it to go to is 1,500. There's only one variable in that, T.
Is that a negative or is that a point?
That's a point, sorry. It looks negative, but it's growth, so it's always a positive coefficient if it's growth. It's always a negative coefficient if it's decay. But E is not a variable. E is a number. So the only thing we need to do is solve this, but it's an exponential equation. It's not an algebraic equation. And notice that I don't even need to know the 500. He could have just said he plans to invest X amount of money. How long does it take to triple? And I could still do the problem because the very first step is to divide both sides by 500. So you end up getting this.
Yes, sir.
And it would not matter what you started with. You're still going to triple it in this amount of time. Now, do you know how to solve that from there?
Does that use a logarithm?
Yes. In particular, natural log.
A natural log.
Because E is the base of natural log. That's what natural log is. If I write it like this, that's equal to natural log. Log base E is approximately 2.71. So the way you do these is you take the natural log of both sides.
Yes, sir.
That I have on the right side, the natural log of E to some exponent Well, I'm allowed to take that exponent and put it down in front, right? That's one of my
Yes,
rules
sir.
of logs, is that if I have something as an exponent, then I can bring it down and put it in front of the natural log of e. What's the natural log of e equal?
Yes, sir.
What's the natural log of e equal?
That is 1.
Correct. So that goes away. And now we have an algebraic equation. And t
Yes, sir.
becomes natural log of 3 divided by 0.0825. You can get that out of your calculator, and that'll tell you exactly how many years it's going to take him to triple his money, whether he started with 500 or 100. Wouldn't matter.
Yes, sir.
So I don't know if you want to come up with a number for that. It's always nice to make sure you have a positive number. You don't want to come up with a negative
Yes,
number. You've done something wrong if you come up with a negative number. This example they're doing up here is exactly the same. They started with p, a equals p to the p times e to the RT, and they just plugged in different numbers. Their rate was 0.08, but the way they did it was identical to the way I did it.
Yes, sir. The answer is positive. I think it is 13.32
Yeah,
years
that
approximately.
also is a ballpark, 13.32. Notice that the example was how long does it take to double, and the answer was 8.66 years. So for it to triple,
Yes,
it's got to
sir.
be bigger than, and the rate was pretty much the same, 0.08. Ours was 0.0825, but so 13.32 sounds correct, makes sense.
Yes, sir.
Okay. Let's look at number 2.
Yes, sir.
Let's set it up. So this is also going to follow this formula.
All right.
This is what makes E such an important number, is that so many processes are defined by it.
Yes, sir.
So what's the first equation I can write?
So is A is going to be 326, right?
Uh-huh.
P is 40. E is E. K in this instance would be R. So R, and
That's what they
then
want us to solve for. Now what do I write now? What's T?
120 minutes.
Okay, this brings up a good thing. T can be in whatever unit you want it to be. It can be in minutes,
Yes, sir.
it can be in days, it can be in years. The only thing that's necessary is that the R that you are solving for be in the same time frame. So if we're going to put this thing in minutes, in other words, I could have written 2 and had it in hours. But then what I would have come up with would have been an hourly growth rate. Well,
yes, sir.
Since they gave it to us in minutes, let's leave it in minutes. And now the R that I come up with is going to be in growth per minute.
Yes, sir.
That's my first step.
All right. Divide both sides by 40.
Yeah, you're always looking to isolate that. Okay, so what is that? 80.
That is
820 0.82.
Do we want to
What's 326 divided by 40? Oh, it's 8.2.
8.15.
8.15. Okay. So that's now equal to this.
That's right.
Next step.
So take the natural log of both sides.
And then you're going to get to a point where when you see that, you know it's always equal to the exponent, no matter what the exponent is. So
Yes,
I
sir.
can immediately write 120R
That's right.
equals natural log of 8.15. So what's R equal to?
R is equal to the natural log of 8.15 divided by 120.
Yeah. Pretty basic, all of these. Let's go on. I know you know how to get that number. Let's see if we can find one
Yes,
that challenges us a little bit more. Let's set up the next one.
yes, sir.
Now that I know you know how to solve them, we don't necessarily have to solve them, but set it up. Give me an equation.
Okay, so it's going to follow A equals P RT. So 12,000 is equal to 40,000 times E, and since it's depreciating, is it going to be negative R?
Yes, just like that.
Okay, so negative 0.12 T.
Okay.
So divide.
Go ahead, give me a number on the left side after you divided everything by 40,000.
All right. Hold on.
It's 0.3, I think.
That's going to be 0.3 equals e to the negative 0.12 t. Take the natural log of both sides. You get the natural log of 0.3 is equal to negative 0.12 t, and you get t is equal to the negative natural log of 0.3 divided by 0.12.
Yeah, now let me just give you a little heads up. When you take the logs of numbers greater than 1, you get positive numbers. When you take the logs of numbers between 0 and 1, you get negative numbers. So we got exactly what we're looking for here. That's going to be a negative number. We're dividing it by a negative number. We're going to get a positive t.
That's right.
So what do you get when you take natural log of 0.3 and divide it by negative 0.12?
So is that around 10?
Makes sense. I would guess that it would take 10 years for a $40,000 car to depreciate all the way down to 12,000. And
Yes.
Here's how things have changed.
Yeah.
When I was a kid, my father used to teach me that when you bought a new car, it lost 1/3 per year. And that was probably true back when it was Fords and Buicks. They probably did lose 1/3 per year because they were made so poorly. But in this day and age, they make cars to last.
That's right.
So this depreciation rate is probably much more realistic for now, for this period of time.
Yes, sir.
In fact, I'll bet my car hasn't. I've had my car for 10 years, but I only paid $15,000 for it, and I guarantee you it's worth at least $5 now. maybe 8. It's a Hyundai, which means I'm getting a depreciation
Oh.
rate a lot less than 12% per year. So anyway, let's see. That takes care of those. Let's have a look at this last page here.
All right.
I haven't had a chance. Oh yeah, this is just the binomial expansion.
That's right.
Interesting. All this n factorial stuff over there. Okay. Let's see. We got 15 minutes. Do you know how to do 1a?
It is, I cannot remember exactly how. Okay. It involves Pascal's triangle, right?
Well, yes and no. That's really the harder. Let's use the binomial theorem.
Okay.
Oh, hold on. Oops, sorry. There, can you still hear me? I knocked over my microphone.
Yes, sir.
Okay, cool.
I can hear you.
The binomial theorem says if you expand x plus a to some power, n, an integer power, what you get is n choose 0. You know what that means?
N choose 0. Is that a combination?
Yes, it's a combination. Not a permutation, but it's a combination. And it turns out that all of these coefficients of the expansion are n choose. Here, let me write the next term. Plus n choose 1 times x to the n minus 1. The x term counts down. And then you have an a term to the 1. And then the next term, and I'm not looking at the book here because there's a pattern here you want to recognize. Dot, dot,
and then eventually
dot, and the final term is n choose n times x to the 0 times a to the n. And if I want, I can even put an a to the 0 in that first term. It actually makes more sense if you do it that way.
Yes, sir.
Notice the x term starts at n and counts down by 1 until it gets to 0.
Yes, sir.
The a term starts at 0 and counts up until it gets to n.
That's right.
Okay, so let's do this one right here. We know what x is and we know what a is.
That's right.
So, what's the first?
The first is going to be 4 choose 0.
I'm going to put it in parentheses. That's x. So it's x to the 4th.
To the 4th.
Okay.
Do we want to include negative t cubed to the 0, or do we just want to?
We don't need to do that because no matter what a is, this is always equal to 1. And that's why you don't usually see it. In other words, not very many people write it in the binomial expansion because it's always 1. The only reason I like to write it is because it establishes the full pattern all the way from beginning to end. And it makes it easier to memorize it. Okay? So what's the next term?
4 choose 1 r squared to the 3rd times negative t cubed to the 1st.
Perfect. And you just go on that way.
That's right.
Now, what's that equal to? 4 choose 0.
4 choose 0 is equal to, so with a combination, it's the 4.
Let's do the general. You need to remember the general.
The general.
The general being n choose r. What's that equal to?
N choose r is equal to n factorial over, is that n minus r factorial?
That's for a permutation right there. For a combination, you need another term in the denominator. And the way I always remember it is it has 2 n's and 2 r's in it. So what else do we need?
Times r factorial.
R factorial. So for our 4 choose 0, we get 4 factorial divided by 4 factorial times 0 factorial. That's equal to 1. 0 factorial, believe it or not, is the same as 1 factorial. I've always found fascinating, and I don't quite understand it. I always used to think they just defined it that way to make everything work. Well, I suspect there's a lot more to it than that. But it is true that 0 factorial is equal to 1, even though it doesn't seem like it should be. So this is equal to 1. Likewise, the very last term, which is going to be 4 choose 4, that's also equal to 1. So this n choose 0 and n choose n, it's always the same number.
Yes, sir. It's always 1.
Yeah, it's always 1. Just like, no, I don't know. I think 4 choose 1 is the same. Yeah, 4 choose 1 is the same as 4 choose 3. Notice why. 4 choose 1, this one right there, is 4 factorial over 3 factorial times 1 factorial. Well, 4 choose 3 is 4 factorial over 3 factorial times 1 factorial. So yes, 4 choose 3 is the same as 4 choose 1. And it's like that with the chooses. Even if it's a 5 choose 2 is the same as 5 choose 3.
Yes, sir.
Because it results in the same factorial in either case. Now, yes, there are some interesting factorial problems on this page. So anyway, expand and simplify, you would just go all for 5 terms.
Yes, sir.
It's always going to be 5 terms when you're expanding to the 4th power. Just like if I had a plus b and I expanded it to the squared, I get 3 terms. So you always have 1 term more than the power you're taking it to.
Yes,
the
sir.
binomial theorem tells you that also. So these are basically just plug in.
That's right. Okay.
Same with B. Same with 2. Just plug in that at x. Plug in minus x to the minus 2. 3, that's a little trickier doing that. And not really. I guess I could write 3 as 1 minus 0.02 to the 12th power.
So you would just plug that in.
Yeah, there'd be your x, there'd be your, or first one would be your a, the second one would be your b. I usually start with a plus b to the n power. most books have it as a plus b. The one book I'm looking in right now actually uses x and a. That's why I used x and a. But this would be one way to do it. Not sure
Yes,
that'd be
sir.
a particularly easy way.
Hmm.
Might not be that hard because that's 1. So you're always taking 1 to some big power. In other words, the calculations are going to be relatively easy. Okay, let's look at this down here while we still have a few minutes.
All right.
You know how to simplify that?
Yes, sir.
Okay,
So
it becomes what? 13 times
13 times 12 times 10, 13 times 12 times 11 times 10 divided by 4 times 3 times 2.
Yeah, and now you can just cancel that and put a 3. You can do that and put a 5. In other words, you can divide top and bottom by the same number to simplify it further.
That's right.
And just multiply it out. Your calculator also has a function that lets you get that number directly. Now, the one that's particularly interesting, I don't know if we're going to have time to cover it or not, but it's this one over here on the right.
All right.
Notice that if I had n factorial divided by n minus 1 factorial,
All right.
let's put in some numbers to see what we're talking about. What's 6 factorial divided by 5 factorial equal to?
That is equal to just 6.
Aha. So this whole thing is equal to n, no matter what n is. So this divided by that equals just
okay.
n. And you can also do a similar thing with n plus 4 factorial divided by n plus 3 factorial. And the way to figure these things out is just plug in any number you want for n, like I did. I plugged in 6. Well, that makes the bottom 5, which made the answer 6, which was the n. So there's some tricks that you can apply to simplify that bottom one. Let's try the n plus 4. Let's see, n plus 4 over n plus 3 factorial. If n were 6, it would be 10 factorial over 9 factorial, which would be n plus 4. So this whole thing is equal to n plus 4.
Yes, sir.
Just in case I wasn't clear. N plus 4 factorial divided by n plus 3 factorial is equal to n minus n plus 4.
Yes, sir.
Yeah, that makes sense. If n divided by n minus 1 is that, then this is equal to that.
Yes, sir.
All right. Some heavy stuff in that session. Well, and we both learned something. At least I hope you learned something. I know I did. On those coming up with the general term. I have never known how to do that. Now I do. So.
Yes, sir.
All right. So let's see. Your schedule for the rest of April through like May 21st is going to be the same as we're doing now?
Yes, sir.
Exactly. Okay. And then starting May 21st or maybe June, I might be off the last week of May. Might not be fully off. I might be available at certain times, but there's a big bridge tournament that I'm playing in that 5-day period. But your mom, I believe, said you were going to try to teach yourself calc this summer?
Yes, sir.
That's an admirable thing. I'm happy to work with you doing that. And I can help you there. I can bring the material to the table almost. I can teach you calc from scratch without following anybody else's curriculum.
Wow.
Which, I mean, it's no different than following a book. It's just that we won't need a book.
Yes, sir.
So, and then the summer, it's going to change from central to eastern or something, somewhere along the way. We don't need to know that right now. My summers are pretty wide open, so you'll have a lot of flexibility for the summer.
Yes, sir.
Okay. Incidentally, Pascal's triangle is the same thing as those coefficients on the binomial expansion, oddly enough. If you look at Pascal's triangle, you can put every number as something, choose something else. Very top is 0, choose 0. The next left, lower left is 1, choose 0. The next one down left is 2, choose 0, and so forth and so on. And that creates Pascal's triangle.
Where the outside on both sides is always 1.
Right. Right.
And the opposing sides are always symmetrical.
Right. And every term is the sum of the two terms above it. So the way you actually create Pascal's triangle is different, but it turns out that everything can be expressed as a combinatoric. Yeah, it's fascinating actually.
Yes, sir.
Yeah. And in fact, sometimes you don't have to go through the hard work of the binomial expansion. You can just use Pascal's triangle to find all those coefficients.
Oh. Yeah, that's right.
All right, Garrison, we'll let you go, and I will talk to you Thursday.
Yes, sir.
Okay. Bye-bye.
All right. Have a nice day.
You too.